Okay, that's done. Now I want to share my screen. Now I'm going to pick this one right here. Okay. Go to presentation mode. Can you guys see that okay?
Yes, sir.
Yep.
A couple people missing here. Right. So does anybody have any questions from last week's lecture? We've been talking about precipitation. We've been talking about coherent versus incoherent precipitation. We've been talking about driving force for precipitation. So that is this change in the system of the energy when you precipitate out little particles. It could be, like I said, either coherent or incoherent. And we've talked about the fact that the structure of these particles and how many they are and how big they are and whether they're part of the atomic lattice or not. We've talked about how that all goes into increasing the strength, or can go into increasing the strength of the material, assuming these precipitates are the right size and distribution and coherency and so forth. So this is really a very powerful way at predicting or engineering the strength into a material. So it's neat stuff. We talked about this great program Thermocalc, which is developed in Sweden, and it's, hello Sheng, how you doing? Morning. Sheng Hong, hello. Glad you're with us. Okay, so anyway, we talked about Thermocalc. Thermocalc is a thermodynamic database and predictive software, which helps you fill in, for the most part, the processing to structure link. It can give you all kinds of, given a given set of compositions of a material, different chemical elements you're putting in there. It can help you predict what precipitates are going to form and how many and how big they're going to be and what the distribution of them is going to be. And that's really useful in designing strong materials and materials that have strong strength to density ratios. We gave this example here about producing a castable 4130 steel, and we needed to add silicon to make it increase the fluidity of the steel so that it would go into molds more easily. And we talked about how that would change the austenizing temperature, and you would need to know that to engineer your process method. And you can predict that with Thermocalc because it draws the phase diagrams, like you see here. And then we talked about going into the link that goes between the structure and the properties. So if you can look at a microstructure of a material and you can quantify certain aspects of its microstructure, you can then go on to predict how strong it's going to be. As far as the strength of density is usually pretty easy to calculate, right? That's usually just easily a kind of like a percentage of material times times the density of that material. But we talked about the law of mixtures, as this is a really simple example of filling in that structure to property link. We talked, I think we went through this slide. I think it was the last slide we went through, that carbon fiber is incredibly strong and epoxy is not so strong, but when you mix the two together, you get a material that can be stronger than steel. We showed another example here with, I'm not sure if we went into this one or not, but we showed an example here with aluminum oxide fibers in aluminum. And I think I was going to tell a story about this one. So did I tell you guys a story last time about the brake calipers at Chrysler?
Not yet.
No, you stopped with your autoclave.
My autoclave, okay. So hang on a second, my hands are cracking apart, guys. Part of living in this part of the country, your hands get all crackly. Anyway, interestingly, when I was at Chrysler, was a time back when wheel sizes on cars weren't so big. There was, right now all these cars have these big, 18, 19, 20-inch wheels, and they sell that as something good in the car dealerships, as if that was going to make your car perform better. Actually makes it perform worse, but it looks cool. But back in the day, we didn't have that much space between the brake caliper, or enough space between the brake rotor and the inside of the wheel, and it was hard to package an aluminum caliper in there. So the industry wanted to go light by going from cast iron brake calipers to aluminum calipers. For those of you who don't know, the brake caliper is the device that sits on a brake disc that squeezes the pads to the brake disc and helps stops your car, helps along with the tires to stop the car. So they wanted to go to aluminum because aluminum isn't as strong or as stiff as steel. They needed to make it bigger. I'll talk more about this in the next couple coming lectures, but They didn't have room to package it, so I came up with the idea of making a metal matrix composite where you would stick these aluminum oxide fibers into the critical portion of the brake caliper so that you can make it strong enough and stiff enough, but still keep it small. And you would, because this fiber is hyper expensive, you would just use just a little bit just where you needed it. So here's an idea. So these fibers made out of aluminum oxide are almost 3 gigapascals in strength, which is crazy. And interestingly, when I was preparing this lecture the other night, I was going through the 3M catalog. So 3M is the world's biggest producer, I think, of this aluminum oxide fiber for structural applications. It's called Nextel. Anyway, I was looking at the 3M website, and I opened up one of the downloadable brochures there on their Nextel fiber systems, and this picture came up right here. And this was my project. I couldn't believe it that all these years later, this was 20 years ago, they're actually still using this in their literature to show the advantage of using this fiber. So I was pretty flattered by that. Would have been nice if they told me. I wouldn't have told them no. I would have said go ahead. But anyway, it's kind of cool. Anyway, so aluminum and Nextel fiber, aluminum oxide fiber, make a nice composite material that's very strong, almost as strong as carbon fiber, but pretty neat material. And the challenge is how do you infiltrate a preform of aluminum oxide fibers with aluminum? And the way we ended up doing that was we used a process called squeeze casting. Squeeze casting is a method where you sort of inject aluminum, molten aluminum, into a mold under high pressure, but very slowly, so you don't create much of a turbulent flow, which can result in porosity and low strength. But so we used this process. We created a fiber preform of these Nextel fibers. We stuck those in a mold, stuck that mold in a squeeze casting machine, and then we very gently squeezed the molten aluminum into the mold, filling up the mold and completely wetting out all the fibers. And we were able to achieve very high stiffness and strength. It was kind of a neat project. I can tell you more if you're interested. Okay, this is, I guess, our first new slide of this lecture. So again, designing the structure to property link. We have talked about, again, driving force to form precipitates that then strengthen the material. You get the most effective strengthening when these precipitates are small, coherent, and all over the place. So very well dispersed. You can predict when this is going to happen by maximizing the driving force. The higher the driving force, the smaller the precipitates are, and the more they are uniformly and populously distributed over your material. And this equation here was developed by the Steel Research Group at Northwestern University, and it says that the increase in shear strength that you get from these precipitates is related to the driving force, delta G, times the volume fraction of these precipitates. And I included a little picture down here. This is an aluminum silicon. This is a 4000 series aluminum. And you can see these little black spots. Those are aluminum silicides in an aluminum matrix. Okay, and I think in this case it's close to a 60-60. Well, I take that back. I have to look up the composition. I don't remember what it was, but I think it's probably a high silicon aluminum. That makes sense. Okay, so so driving force can then very easily be correlated to hardness. The higher the driving force to form these M2C carbides, I guess M2C, so this is not M2C, this is aluminum. Okay, sorry. So anyway, in steels, the higher the driving force to form these M2C carbides, the higher the hardness, and then hardness is directly related to strength. The higher the hardness of the material, the higher the strength, although they are different quantities. So this is a great example. This is where you can engineer the material by selecting a composition. Okay, you're putting chrome and moly in a steel. You can choose those elements so that you're maximizing the driving force for precipitation. And then if you achieve this precipitation where you have these very fine, coherent, highly dense network of these guys distributed all over the material in a high density, very numerous, then you can maximize strength. And I need to change this microstructure because it's actually the wrong material. This is a aluminum, like I said, this is a 4000 series aluminum. I really should put a steel in there and show those precipitates. But anyway, I think it gives the picture anyway that lots of little precipitates give you high strength. All right. So again, designing composition, designing a heat treat gives you a material that is the highest strength, You can then understand this microstructure and go from microstructure to strength using this relationship. Another way of calculating the strength or predicting the strength based on the microstructure is the Hall-Petch relationship, which we spoke about in a previous lecture. This says that the strength of a material is inversely proportional to the square root of the grain size. So the smaller the grains, the stronger the material. I've used this equation a couple times on nickel tungsten coatings. It holds up pretty well. And this is an example of a tool. This is an example of a tool that fills in the structure to property link. Okay, so in the past several lectures we talked about the processing to structure, and now we're talking again about the structure to properties. So we've completed the 3 chains, which is the fundamental goal of material science, I think. Okay, there has been a tremendous amount of work, and there's a tremendous body of literature out there, that's been written within the past maybe 5 or 10 years on creating models that predict the strength based on what you can see in the microstructure. And a nice body of this work was completed under the Accelerated Insertion of Materials program, which was funded by the Office of Naval Research and the Defense Advanced Research Project Agency, DARPA. So you have watched the X-Files, you probably know DARPA. And a lot of this work was done at Questech in Evanston, Illinois, to develop these models. Now this model over here, this yield strength model you see, this was developed under the AIM program, and it's really complex. This is a real headache to look at. This isn't something I'd want to try to calculate by hand. This is, I think, something you write a computer program from and then put in a couple of key inputs and let the computer worry about it for you. But this equation here takes into account solid solution strengthening, which is something we've talked about, right? It takes into account the Hall-Petch relationship. This gamma phase that it has listed right here, gamma is a precipitate phase, okay? And then it takes into account shearing of particles, all kinds of crazy stuff here. This is a very complicated program. This is, I think, really the cutting edge of predictive material science. So predicting strength from the microstructure. If you guys want to learn more about this, I recommend you go to the library and look it up under Professor Olsen or Questech. I'm going to do it actually because I would like to learn more about this equation. But there are several papers out there that have similar types of equations. I've read a couple of them. They're hard to understand. They're dense, pretty dense full of information. But the point I'm getting at here is that there really has been a lot of work in developing these structure to property links. Producing predictive models that can be run probably on Excel to do this calculation. Unfortunately, the thing is that as I tell people, the processing to property link, processing to structure link is much better filled out, and there's much more capability in there in terms of commercial software, in terms of good predictive models that can go between processing parameters and microstructure. That link, I think, is pretty well populated. The link that goes from property or from microstructure to properties, not so well filled out. And there's, it's really amazing. You take a material, you polish it up, you etch the heck out of it, you look at it under an optical microscope, or you look at it under a scanning electron microscope, or if you're really rich, a transmission electron microscope, and be able to look at that, take a couple key parameters perhaps from that microstructure, and then be able to calculate out a strength from that. That's pretty amazing. Now, when I say it's not real filled out, what I mean is that there is perhaps some good modeling done there already, and some good predictive models for yield strength, or even tensile strength, and maybe even a little bit of stiffness, but there's not much there for many things else. I mean, there's not a lot of work done, for example, predicting energy absorption from the microstructure, or predicting fracture toughness from just looking at the microstructure, or I don't know, different magnetic properties. These models are not quite as well filled in as they are with yield strength. It's the yield strength is probably the most mature predictive model in that structure to property link. Any questions, guys? So you're gonna run to the library and look this up? Anyway, good stuff. Complicated, bring some coffee. Right, so we've been focusing on these two quotients. strength to density ratio and the stiffness to density ratio as tools we can use to create the lightest, most efficient structures. So we've talked about yield strength to density. Now we're going to talk about stiffness to density ratios. This is the other quotient that we said was critical in making strong structures, or most mass efficient structures. Okay. Again, it's a system, processing structure properties. There are subsystems to these systems, and they link together and back and forth between each other, and you can engineer those subsystems and systems to maximize stiffness to density ratio to some extent. It's not quite as you don't have quite as much freedom as you do with strength. But so here is our systems diagram. Okay, 3 examples of some subsystems that can be used to stiffen materials. You can stiffen materials, for example, through fiber reinforcement, through particulate reinforcement, so little particles that you stick in there. It's like a Duralcan aluminum material, if you've heard of that. And then here, you can also do it through alloy, so like aluminum lithium, which we'll talk about in a minute. I wanted to give you a little bit of fundamental background on what drives the stiffness or the Young's modulus of a material. First, I'll say that stiffness is something that as engineers we should know what that is. We should also, I think, any mechanical engineer or material scientist should know that there's this thing which is Young's modulus, which is the stiffness, the slope on the stress strain curve. What's not necessarily explained at the undergraduate level is that Young's modulus is the stiffness of a material that is isotropic, meaning that the mechanical properties are the same in every direction. And actually there are, some, I can't remember the number, 54, something like that, independent stiffness constants for a material that has no anisotropy, that's different properties in every direction. But we're just going to say stiffness just to talk about, this concept of how much force or energy does it take to separate the atoms in a material. So I'm going to talk like a physicist here for a couple minutes. Hope you don't mind. But the stiffness of the material is determined by interatomic forces. So physicists like to talk about you have some huge vacuum and there's these 2 atoms and one's way the heck over there and one's over there, and somehow they sort of spot each other and they begin to move each other because there's this attractive force between these atoms, and they get a little closer, a little closer, a little closer, a little closer. They get closer, 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 closer. Eventually they get to a point where they hit some equilibrium because there's this attractive force which is pulling together, but at the same time there's this electrical charge that, there's this electrical force that's pulling them together, this electrostatic attraction. But then at the same time, if they get too close, there's an electrostatic repulsion. So it's sort of like having 2 negative charges next to each other. They begin to repel. So there's one force pulling them together, and there's another force pushing them apart. And then there's some place where they kind of just hit an equilibrium, and they stick at this distance from one another. Okay, you guys probably saw this in, I don't know, maybe one of your physics classes in undergraduate. Yes or no? Okay. Oh, Wu's shaking his head. So these things they find some position together. Okay, this graph on the far left here, this is sort of an approximation. It shows that as the interatomic distance is decreasing, the repulsive force is I think I got this backwards. The repulsive force is I do have this backwards. Sorry. Oops. Sorry, these are switched. The repulsive force is increasing and the attractive force is decreasing, and they reach some equilibrium. Okay, when you take the forces from the repulsive, this is a potential energy graph. So as the atoms get to this sort of equilibrium position, the potential energy of the system hits some equilibrium value. And if you take these 2 repulsive and attractive graphs and you add them together, you can think of this thing called the potential well. It's given by this graph right here. And when the potential energy of the system is the lowest, right here, that's where you find your equilibrium position. For those of you who've taken a lot of physics courses, you know that the derivative of the potential energy is force. Okay, and now that we have force, we can think of the slope of that force curve as being some measure of stiffness. So looking at this material 1 right here, right, we've got this potential well. Okay, and then we take the derivative of that and we get this graph right here, and then the slope of this graph is equal to the stiffness, which is then For an isotropic material, meaning the properties are the same in all directions, for an isotropic material, the stiffness is the slope of this curve. So the red line right here, the slope of that line is related to the stiffness of the material. Now, some materials, actually, I keep trying to move around this picture, you guys here. Here we go. All right. Some materials have different shape potential wells. So the shape of this potential well changes for every element. It's different for two aluminum atoms together. It's going to be different for two iron atoms coming together. It's going to be different for two lithium atoms coming together. The shape of this potential well changes when you start alloying a material. When you take carbon and you put it in steel. When you take aluminum, you put lithium in it. When you take magnesium and put aluminum in magnesium, the shape of these potential wells gets altered. So it's an electrical potential that's changing, okay? When you get a steep, deep potential well, like this one I'm showing here on the left, I'm sorry, on the right, material 2. Okay, when you look at this guy right here, this has a much deeper, sharper potential well. And when you take the derivative of that, you get a steeper curve for the net force. See that? You get a steeper curve. The steepness at the position where this is a little misdrawn, where it crosses 0 for the force, the slope right there is related to the elastic modulus of the material. So I hope you can see where I'm going with this. As a materials engineer, you can then start mixing different materials together that alter the shape of this potential well and increase the stiffness. And that's where the engineering part of this comes in. This is good fundamental information. And by the way, the melting temperature of the material is also related to the shape of this potential well. The deeper and sharper the potential well is, the higher the melting temperature. So Young's modulus and melting temperature have some loose correlation between the two. Guys got this? It's a thing you can follow around for a long time. It can be useful in many applications. So just remember this potential well. Okay. Aluminum lithium was kind of invented in the 1980s. This is an alloy of aluminum with a tiny bit of lithium. The lithium atoms are pretty close to the same size as the aluminum atoms, so they'll take up positions on the aluminum lattice. So it's a substitutional solid solution. It's pretty expensive still, I think, at this point, and it's used in aerospace. And when you start thinking about stiffness to density materials or strength to density materials, it's pretty amazing stuff. For every 1% of lithium that you add to aluminum, the density goes down by 3%, and the stiffness goes up by like 5 to 6%, the Young's modulus. So you think about that quotient of E over rho, and the denominator is going down and the numerator is going up. So you can see all kinds of potential there for increasing the strength to, or the stiffness to density ratio and engineering this material. The stiffness will increase, okay, as you're adding the lithium atoms, okay? It'll increase, and still stays a solid solution, right? Still stays a solid solution. So you're getting stiffness purely from changing the electrostatic nature of this lattice, up to about 4.2%. Where's my cursor? Up to about 4.2%. And then you get these little Al3 lithium little precipitates, coherent precipitates begin to precipitate out of the matrix. And the increase in stiffness begins to, with adding lithium, begins to decrease. So the slope is going down here compared to here. It's stiffer here than it was there. But you still have an increase in stiffness. And typically, I think the products that you see on the market, most of the products you see on the market that maybe you can buy commercially of aluminum lithium, they have probably no more than about 4% lithium, maybe closer to 3% lithium. And there are some aluminum lithiums that you can buy out there that are precipitation strengthened. And like we saw before from steel, this material is very has very high potential to strengthen by precipitation hardening. Right, so you get these coherent little particles that precipitate out, and then all the stuff we talked about before about how this affects the strength of the material. Okay, that can get all that, and you can also get an increase in stiffness. So aluminum lithium is kind of a wonder material, and back in the 80s, it was a lot of research going on in this area. Enrique Lavernia, who was a graduate student at MIT at the time, did a lot of research in this area under Nick Grant, and then he later went on to University of California, Irvine, and did a whole lot of research on aluminum lithium, and wrote some great papers. It's Lavernia, Enrique Lavernia, Lavernia. Brilliant material scientist, and did a lot of work in this area. Really, really interesting material. This is probably a material we should start thinking of making bicycles out of, by the way, Steve, except I think, I got to look into this more, but I think it's not the best from a corrosion perspective. So it might corrode very easily. It might need a lot of coatings, but it's probably expensive too. Someone have just heard a weird sound. Okay. Another material, another way we can engineer the stiffness of a material is by using or looking at some of these high silicon grain-oriented electrical steels. So when you make an electric motor, you have these laminates that they use. They stack up these laminates, these little steel laminates that they typically stamp, these flat laminates. They stack them up and they mount wires to it or motors, depending on which side of the stator or the rotor of the electric motor it is. But these high silicon steels, they focus, they act like a lens to the magnetic field in an electric motor. So they give you higher efficiency on electric motors. And I think AK Steel is the 800-pound gorilla in that market. They sell a lot of this material to motor manufacturers. And something I happen to notice or come across by accident with this material, which I don't think has been discussed much in the auto industry, is that the high silicon steels have a higher Young's modulus by a good amount than do just straight steels or low carbon steels or even high strength steels. So it's interesting to me that the steel industry for automotive has focused for the past 20 years on increasing the strength and formability and toughness of their steels. They have all these ultra high strength steels, advanced high strength steels that they have very effectively sold to the automotive industry, okay, to give them materials that will outpace aluminum in strength to density ratio, okay, but still be formable. So that the steel industry is in a constant war with the aluminum industry in how it pertains to automotive, because cars are trying to get lighter, so the natural tendency is to gravitate towards aluminum, like the Ford F-150, a big pickup truck. So the steel industry fights back by coming up with ever higher strength steels. And they've done a great job of it. And when you're in parts of a vehicle or a car that you're solely designing for strength, in a lot of cases, you can build a lighter structure from steel than you can with aluminum, because the steels that they offer have such incredibly high strength. But they really haven't said much about stiffness. So I came across this thing with the high silicon steels by accident. And as you can see here, this little table I've got at the bottom, the stiffness of steel is about 200, 210 gigapascals, okay? That's like, you know, stainless steel, ultra high strength steel, low carbon steel. It's all somewhere between about 200 and 210 gigapascals in Young modulus. But this high silicon steel that they use in motors has a stiffness of 258, almost 260 gigapascals. And I think I couldn't find it when I went back and looked for it, but I think I once saw something as high as about 275 gigapascals in stiffness. So this is pretty interesting. All of a sudden you've got a, you know, what is that, like 20% increase in stiffness of your steel, which for design for stiffness applications can mean a lighter, stiffer structure. So the problem, however, is that when you start adding silicon to steel, you suppress what they call the austenite loop. So the austenite loop is that field on the phase diagram that you heat to in order to solution treat a steel. You know, we talked about several slides back, or several lectures back, we talked about heat treating steel. You know, you solution treat to this temperature. It goes from body center cubic to face center cubic. It becomes austenitic. You quench and freeze in that microstructure, and then you can create martensite. And martensite is strong. That's good. imagine what would happen if you could never austenize the material, because by adding so much silicon, you suppress the austenite loop. You would never be able to heat treat this material to make it strong. So I was playing around on thermocalc the other night, and I was noticing that as you add nickel, because nickel is a known austenite stabilizer, as you add nickel to the high silicon steel, this austenite loop, which is right here, begins to grow. So here's 0% nickel, here's 1% nickel. You see it's gotten a lot bigger. 2% nickel, it's gotten a lot bigger. And at a 3% silicon, by the time you've got 3% nickel, it's feasible to get into that austenite loop right here. So again, this is the austenite loop. Okay, this is for a 3% silicon steel. And as I've added more nickel, that nose has gotten bigger. It's grown. See that? So now it might be possible to quench this material and get martensite. You could have a high silicon martensitic steel. And then you could start thinking about using it in structural application because it's strong. You couldn't do that with just a normal silicon steel. So this is an example where we've added silicon to increase the stiffness of the material. We've engineered, by choosing a composition, we've engineered a higher Young's modulus to density ratio material. We found a problem with it, okay, that you can't austenitize, you can't solution treat it and make it martensitic unless you start adding nickel. So here's a way where we're engineering this material to do the things we need it to do. We're you know, initial look was that we would have to trade off stiffness for strength, but maybe there's a way to get it back by adding nickel. So I have actually discussed this project with Professor Greg Olsen, and he warned me that you'll precipitate out these iron silicide particles, which are brittle. And so I need to go back and look at that. Maybe this is the next step in my little project here, is to figure out, is there a way to decrease or suppress the driving force for these aluminum silicide particles and increase the driving force for the M2C particles. But anyway, here's like I said, this is an example. You've engineered the property, or sorry, you've engineered the microstructure to properties link by adding silicon to increase the stiffness. So the next question is predictive models, going from the microstructure to predicting the stiffness of the material. I'm going to fall back on this example, the law of mixtures from composite materials. The two equations here are the law of mixtures for calculating out or predicting the stiffness of a composite material for both, in this case, for continuous fiber reinforced material and for precipitate reinforced material. Pretty simple equation. It just says the stiffness of the of the reinforcing fiber times the volume fraction of that fiber plus the stiffness of the matrix times the volume fraction of the matrix gives you a predicted stiffness for that material. And then there's a similar equation below it, again, for precipitation or for particulate reinforcement, except there's a correction factor K here, which helps you predict the again, the stiffness for this material. This should probably be a P right here. Sorry, guys. Oops. And I've gone through and I've given you some examples. Carbon fiber, epoxy, right here, with assuming a 40% volume fraction. The stiffness of the matrix isn't very high. It's only 3.1 gigapascals. The stiffness of the carbon fiber, 230 gigapascals. You combine those two together, and you get a material with a stiffness of almost 94 gigapascals. So notice that that's about half a steel. The composite I made with 3M back in the day, aluminum oxide fiber and aluminum oxide Nextel fiber in an aluminum matrix. Again, I think we were able to hit about 40 volume fraction percent. The stiffness of the matrix, aluminum is about 70 gigapascals. The stiffness of the, note the stiffness of the fiber here was amazing. It's 373 gigapascals. That's the stiffness of the fiber, so incredibly stiff. Stiffer than carbon fiber. A boatload more expensive, but definitely stiffer. You mix those two together and you begin to get an aluminum that has the stiffness of steel. If we were together in class, I have some actual little panels of this material that I like to pass around for people to play with. So I've got two panels about this big, or three panels about this big, all cut about the same size and the same thickness. One is made of steel, just a low carbon steel. One is made of aluminum, and one is made of this aluminum oxide fibers and aluminum, this Nextel material. And you can, when you bend these materials, the steel you can pretty much bend past yield. Okay, the aluminum one you can do the same, and it's not very stiff. You can get it to move pretty far. But then you pick up this other material, which just looks like aluminum, but it's reinforced with these Nextel fibers, and it is so stiff you can barely move it. It's just amazing. And again, this is crazy expensive stuff. If you use just a little bit of it in the right place, use the fiber like spice, as some people have said, then you can get a cost-effective stiff material. Another example I wanted to show here is a material that was developed by Toyota. This is a steel reinforced with titanium diboride particles. Titanium diboride particles are incredibly stiff, 510 gigapascals, incredibly stiff material. It's hard to get much of a volume fraction in the steel, and I don't really know much about the sort of interface between the two, if there's good adhesion between these titanium diboride particles. But the volume fraction is, maybe can get to about 20. And, matrix of steel about 200 gigapascals, and then again, this 510 gigapascal titanium diboride particle. You put those two together and you estimate the stiffness of this material is a good bit stiffer than steel, 270 gigapascals. A note, by the way, here, guys, that, as I said in this previous slide, where was I? Right here, the high silicon steels. This stiffness right here is now approaching the stiffness of its composite without having to form a composite. So interesting, need to look into this further. But anyway, you can see this is a material that was made by Toyota. It's probably really expensive. It didn't go into production because it's really expensive to make, but it proves the point. It shows that here's a predictive model to get you from the structure to the properties relationship. This program is called OOF, OOF2, OOF3. Funny name. It's called Object-Oriented Finite Element Analysis. This was developed at the National Institute of Standards and Technology, Gaithersburg, Maryland. I think it was developed in the early 1990s, and it's kind of neat. I've used this program a couple times actually. You can download it for free from the NIST website. But what it allows you to do is you can take a microstructure that you got off of an SEM micrograph or an optical microscope. You can take that microstructure that you get the image of it, and then you can put that microstructure or the micrograph of that microstructure into OOF, and you can then mesh the microstructure, and it'll break it up into the different particles or phases or grains or whatever. You can then mesh that microstructure, and then you can assign mechanical properties like stiffness or strength to the particles, and you can break it up based on one strength and stiffness for a grain, and maybe a different strength and stiffness for a precipitate or a fiber, something that's in the microstructure. You can then assign different properties to each of these different phases that are in the microstructure. Once more, you can also begin to assign orientation. So as I said before, like you take a piece of steel and you stretch it in different directions and you get the same stiffness in every direction. It's an isotropic material. But if you looked at a single grain of steel, it's actually anisotropic. It has orthotropic properties. So the stiffness in one direction, is one number, and then you go perpendicular to that, and it's a different number. Okay, and you don't see that effect because when you get a piece of steel, all these grains are oriented in random directions. So the far field stiffness of the material is one value. It's isotropic. But at that really small length scale, when you look at individual grains, it's anisotropic. You can model this anisotropy in OOF. So you can take an individual grain and you've taken, from your micrograph. You can take an individual grain and you can assign an orientation. So you can assign the stiffness vector or the stiffness quantities in each direction for that little grain. Okay, and then what the neat thing is that you can apply boundary conditions to this mesh of different grains and precipitates and fibers or whatever, and then it will give you what the overall value would be for that whole assemblage of grains or fibers or precipitates or whatever. So you can begin to use OOF to calculate out the stiffness, the bulk stiffness or bulk strength of a material by using a microstructure. So this is a great example of how you fill in the structure to property link. I use this actually as a, let's see what time is it, guys? We're almost out of time. I use this software when it was in the beta phase at NIST. And I was, when I was a graduate student, I was working on a project where we had these little, it's called iron titanate particles. And these little iron titanate particles, grains effectively, they were paramagnetic, so that when you stuck them in an electric field or a magnetic field, if they were free to rotate, like if they were suspended in some ethanol, say, you stick these things in a strong magnetic field, and then the particles would align. So the grains of the material would align. So by doing this, I can make little pieces of material, and each one had different elastic properties, but it was the same material. So I found a way to lock in the orientation, or I should say, my lab mate, Michael Zimmerman, found a way to lock in the orientation of the particles. Okay, I found a way to laminate the different little sheets of these oriented material together, and then I could form residual stress fields in these materials by tweaking around the orientation of these particles. But I used OOF to estimate the stiffness as a function of the orientation of these little particles, these little grains of the iron titanate. And I was able to get pretty accurate. You know, I would do a simulation and then test a real piece of material and get values that were pretty close. So
Don, may I ask a question? I'm sorry to ask you to go over something again that I.
No worries.
Could you explain again the significance of materials being isotropic and anisotropic when it comes
anisotropic.
Non-iso, yeah.
Okay.
When it comes to the stiffness?
Sure. So so isotropic means that the properties are the same in every direction.
Everything's aligned, right?
Right. So if you have you have a block of material, you can see my phone here. Suppose this is just a block of steel. You can expect the stiffness to be the same in this direction as that direction as that direction. The stiffness is the same in every direction.
Okay.
If you take a piece of carbon fiber, suppose this was carbon fiber now.
Yep.
The stiffness and the fibers were aligned in this direction.
Yep.
You know, like along a top tube of a bike frame.
Yep.
The stiffness in this direction can be dramatically different than the stiffness in that direction.
Got it.
Okay.
Yep.
And this is critical because, for example, when you're building a bicycle frame and you know the loads are you know what the loads are, right? It's very well defined. You know you want the top tube to be stiff in tension, for example, or compression. So you put the stiffness only where you need it. You don't have to waste material and weight and capability putting it perpendicular where you don't need it. So perpendicular to a tube on a bike frame.
As opposed to a bottom bracket, which is going to require, it's going to be subject to all kinds of rotational forces.
Exactly.
And so you need stiffness in almost all directions that way.
Exactly.
You might lay your carbon fiber down this way and that way.
Exactly. Or you just use, I think what they do in that case is they have like I don't know. I think I'm going to buy a carbon fiber giant frame or Trek frame or something. I'm going to cut it open, bring it in next semester. So I'll get one that's been crashed on eBay or something for $100, and I'll cut it up. We can take a look at it.
That's where the science stops, I think, and the art begins oftentimes.
Perhaps. We'll talk about that later on. But anyway, the point being is that individual grains, like I've shown you these microstructures of grains of materials, right? Individual grains, because there's effectively a single crystal of material, they are anisotropic. They have different stiffness values in different directions. When you solidify a piece of steel or aluminum, these grains are oriented at all these incredibly random orientation typically, and then that means that the far field stiffness, the bulk stiffness of this material, is isotropic. When you heavily roll a piece of steel, okay, and you use these various heating and quenching and cooling operations that they do in the steel mills, you get what's called textured material, which means that the grains have a somewhat common direction. It's not perfectly lined up or really highly lined up like I was able to do with my iron titanate materials as a grad student.
Like
yeah.
waves.
Huh?
Like waves?
Maybe. I don't know. There's ways I've done this before. There's ways of using X-rays to measure the orientation of the grains in a piece of steel or a piece of aluminum or a piece of whatever that's crystalline. I've never, and the graph is called a pole figure. A pole figure tells you the amount of crystallographic alignment that you get between these various grains in a piece of material. And I've never seen, well, I have seen, I don't remember, I've seen them, but I don't remember what they say. Anyway, there are pole figures that show you the alignment for rolled steel. And certainly the steel companies have people that do this X-ray experiment where they measure the alignment of the steel. But the point I'm getting at here is that you can go from knowing that microstructure to the stiffness of the material using this program from NIST. So you can, any one of you guys can download this program if you're interested in it, and you can look it up on the internet. I'm sure they would, you know, they're altruistic people, I guess. They love to see this material and their program in use. And I'm trying to download a copy.
The taxpayers paid for it. It's from the United States Department of Commerce. That's why it's free.
Hey, it's a good use of money as far as I'm concerned.
Yeah.
I like to hear about my taxes going to places like that.
The Bureau of Standards, you know?
Yeah.
You already paid for it.
It's a good thing. So take advantage of it, guys. Okay. I think we're just about out of time. This is lifted from Greg Olsen again, and we'll probably get deeper into this, but this is a very interesting graphic. It shows the different length scales of a material going from really small at the atomic level at the lower left side to the upper right side where you're looking at more sort of centimeter scale casting simulations. Okay, so it shows the different tools that are available to fill in the processing to structure link and the structure to properties link. So all these acronyms here, these are little names and things. These are computer simulations, computer-based predictive tools that you can use to fill in those links. And to tell you the truth, I don't know all of these. I know some of them. TC is Thermocalc. I've mentioned that to you guys already. Dictra is a software that predicts diffusion of atoms. For example, if you're hardening the surface of a material through a process called carburizing. And Abacus is a finite element package that can be used to predict strength. In this case, this is similar to what the OOF program is, where you can use finite element analysis to go from microstructure to bulk properties. And then there are some casting simulations, some simulations of martensite material. So those are all these acronyms over here. Okay, going down the other side here, I should mention, so these are atomic scale. These are sort of electron potential simulation of atoms that are coming together. I think this is steel with phosphorus. And this is microstructure, this is precipitates, this is the next length scale up of martensite lath particles and grain boundaries. And then this is a full-size casting. So you're going from the atomic level, angstrom level, all the way up to pretty much the macro scale up here. Going down the left side of these images, these are different tools that you would use to look at these microstructures. So I talked about X-ray before, X-ray diffraction. That's XRD. Small angle neutron scattering for looking at atoms. And also microstructures too. Transmission electron microscopy, you can see columns of atoms. I've shown you some of those pictures before. Scanning electron microscopy, EDS, measures composition. Scanning electron microscopy, you can look at microstructures and more macro things, maybe, you know, down to, I don't know, maybe a millimeter is the biggest thing you can see in scanning electron microscopy. Oh, is that true? I don't know. Most electron microscopes I've used, you really can't go below like 20x. Anyway, this is an interesting, I find this a really interesting graphic, and that's why I wanted to include it, just to show like all the full sort of spectrum, the range of capabilities that the material science community has managed to put together. It's really quite amazing. I think we're out of time, but I was going to introduce the Olsen diagram, which I was going to talk about next time. This is an Olsen diagram for high strength steel. And then I was going to give a little short biography here on Greg Olsen, who you can see here next to his Lotus Elise. He has very good taste in cars. And I'll stop there. Questions, guys?
Thanks for the explanation, Don. I understand the significance of isotropic. I appreciate that. Sorry if I took up too much time.
No. That's what. No, like I said, I've baked in, I think, a lot of extra time, and I want this to be interactive, and that goes for all you folks. Please ask as many questions as you want. It's like I said a long time ago, or a couple lectures back, like I I'm not a good passive learner. I really only learn things by getting into dialogues with people and annoying the hell out of them. Not that you annoy me, but I probably annoyed a lot of my professors, including Greg Olsen.
You wouldn't be the first. You wouldn't be the first.
No, and I've got the patience for it because I understand the importance of it. I don't think Greg Olsen does, though.
All right. Thank you very much.
You're welcome. Any other
See you
questions,
next
guys?
week, buddy.
Okay.
Thanks,
See you next
everybody.
week.
Later.
You got a question?
Yeah, I had a question about the Nextel fiber aluminum composite. Just seems like a pretty awesome set of properties it's got. What are some of its limitations? I'm kind of wondering. I mean, I know it's really, really expensive, but I can think of a lot of areas where price isn't really an object when you've got to get the smallest, strongest thing,
Right.
Smallest, strongest, lightest thing possible.
So the biggest problem is money. This is expensive stuff.
Yeah.
It's really expensive stuff. They use this. There's a lot of like aerospace, spacecraft applications where they do spend the money to use the fiber. I think they use it. You can find the brochure. There's a great brochure on the 3M website. It's expensive as heck. It's expensive as heck, and that's probably why it really didn't go into production, because it was just too damn expensive. Even though we were only using a tiny little strip about this big, really thin, it was still probably too expensive to go into production.
Have they figured out how to produce it in like big sheets or?
Oh yeah. No, if you have enough money, they'll do all kinds of stuff for you, right? 3M loves to use this material. They have, I think they might make some kind of ballistic blankets out of it at this point. I don't remember what the fracture toughness is of the composite. It's something you should keep an eye on. If you think it's going to see a lot of impact loading, it might not be the best option. But for stiffness and strength and weight, it's pretty hard to beat. If you got the money, I think, for example, like the stiffness of the fibers is so high, like you can't use it in Formula One. So Formula One, like they limited the materials that the team used by putting a cap on the Young's modules, actually. So that's how they got the teams from, because the problem with Formula One racing is that people have all kinds of money and they're crazy, and they'll spend crazy banana monies to win, no matter what the payoff is or isn't. And, they'll just buy more and more expensive materials. So like in the early 80s, Honda, which was, Honda was dominating Formula One in the early 80s. They had all kinds of ceramic parts, all kinds of silicon nitride parts in the engines. Cylinder liners, pistons, valves, and the engines were super high performance, but they were just incredibly expensive because of the silicon nitride. So, and another thing is, I don't know, I wrote a paper recently, or a little article published on LinkedIn, if you guys want to go look it up. There's an article on beryllium. So beryllium has a Young's modulus that is like 3 times that of steel. Seriously, beryllium metal has 3 times the stiffness of steel. And the density, I don't remember what I wrote in the article, but it's probably like 1/10 of steel. It's crazy light. You pick up a piece of beryllium and you think you're picking up a piece of balsa wood and you're wondering why it's cold. That's what beryllium's like. It is the spookiest thing I've ever seen. And it's very rare. They don't use it very much because you get berylliosis from it when you machine it. It's highly toxic. Okay, highly toxic. And anyway, that was a material that you couldn't use in Formula One because it was too stiff. That's how they stopped the teams from using beryllium, by putting a cap on the stiffness.
Well, is the aluminum Nextel composite fairly machinable at all, or does it pretty much have to be molded and then,
it's got to be molded to shape pretty much. But the thing about it is that if you can, through doing a finite element analysis, if you can pinpoint, this is where it needs to be stiff, this is where the maximum strain is, right here, then all you need to do is you just put your fibers in there. You don't need to worry about here, here, and here, and here. You just put them right there. Right. So in that sense, that's how you keep the price down, is by using it like spice. You use as little as you need to in order to get the stiffness that you want.
That makes sense. Where do they make it? Where do they do the molds?
So the thing you're going to find is that 3M will be very happy to sell you the fiber. And if your volumes are high, if you think you're going to make a lot of your widget, they'll work with you to try to find a casting house and everything to actually make real components. If you have a one-off application, you're gonna have to fiddle with it yourself.
Mhm.
So I can tell you, like, there's a foundry in Neckarsulm, Germany that we used called Kolbenschmidt-Pierburg. And Kolbenschmidt-Pierburg casts out blocks for Porsche. So the engine block in a Porsche has the cylinder liners are these little porous ceramic preforms. I can't remember the exact fiber, but the cylinder liners, you know, kind of a cylinder, an open cylinder. It's a fiber ceramic. Okay, they stick that in a mold. They put the mold in a squeeze casting machine, and they very gently put in the aluminum and fill up the mold. And the aluminum reacts with the ceramic and forms a really high hardness intermetallic material that becomes a cylinder liner, which is very effective. Toyota did the same thing, or Toyota does the same thing. It did the same thing on the some high performance engine they made. They put it in the Matrix. They also put it in the Lotus Elise. It's like a 1.8 liter little high revving engine because it's so hard. Honda did it, like on the S2000. They used the exact same technology. The reason I'm telling you this is just that if you wanted to make a part and you had enough money to pay for the mold, you might be able to get these places to cast it for you in a squeeze casting machine. If you really want to talk more about this, I know some other foundries in Ohio that might be willing to do it too.
I don't think we'd ever make anything in big enough quantity to make it make sense, but
if you want to pay
very
for
cool to know about.
That's what it comes down to. If you're not trying to amortize the price of the mold over thousands or hundreds of thousands or millions of parts, if you're just saying, fine, I have performance is all that matters, I have to get there, then you can try doing it that way. You might be able to, there's other things you can do. You might be able to encase it in epoxy, then put that epoxy into the cutout in the aluminum or something. There's different things you can try depending on how motivated you are.
Interesting.
Anyway,
if no one else has any other questions, we talked a bit about INVAR before, and I've been doing some more digging on that. I could talk to you about.
Yeah, absolutely.
I've been looking into all of the different heat treatment processes that we use, and talking to different engineers who have made INVAR lectures on why they use certain heat treatment processes for different parts. And so I've been getting a good picture of that, and I was going to try to start looking up some diagrams of some like phase diagrams of INVAR and see what jumps out to me given the temperatures and the times that we take, because I'm not sure exactly what all I'm able to tell you about our heat treatment processes, so I can't quite just spit it all up and ask you what you think until I know that other places out there in the public do the same exact things we do. But just letting you know, I'm digging more into that, and I'm really interested in finding out more about that.
You have the
microstructure.
You can start to think of this in terms of microstructures that you want, microstructures you don't want, phases you want, phases you don't want, and then you can use a tool like Thermocalc. And if you want to get since you're a student, you can get a license to use Thermocalc through MIT. And,
I think I may even be able to just download it on my work computer. I think it might be available to us in general, or I might have to get permission somewhere, but I think I can just download it from our software center, hopefully.
If somebody's
not, then
Hotshot, it's not, you have to get the right database too. Right. So the Thermochemical Database is I think that's one of the more expensive parts, because some poor soul's done all these, experiments trying to figure out the thermodynamics, quantities of these materials at every temperature. I think it takes a special individual to want to sit there and figure that out. But the point being is that all that stuff goes into a really expensive database, because some poor guy's had to sit there for, his whole life and, be paid this amount of money per year and figure out all this information. So that's pretty expensive, but just make sure you've got access to the database as well.
Yeah, I'll see what we have here. And if I can verify that I can just talk to you freely about our heat treatment processes, then I'll probably just do that.
Great.
I'd be really interested to see what you think.
Do you have ICMA people? Do you have people working on ICMA at Lincoln Lab?
I assume so. Yeah, maybe not a lot. Group 74 is kind of our analysis group in the engineering division, and they're the ones who run a lot of the simulations on, well, about any of our FEA, all of our thermal simulations. They pretty much all goes through them, and I don't know if they really think too much about tailoring materials, or a lot about the material science, unless they really have to. So I'm not sure if that's going on in the lab or not.
Yeah, I mean, I took my undergraduate education was in mechanical engineering, so I'm not disparaging mechanical engineering, but I can say that you're taught to look up values in a table, you know, and that's like I said, that's kind of the domain of the mechanical engineer. The materials engineer is to say, okay, tell me what you need, and we'll see how close we can get there, right? And unless you've got a large materials engineering staff at Lincoln, which I don't know, it wouldn't surprise me if they're using tables and so forth. But you're sure that Thermocalc was in your sort of I don't know, cache of different programs that you're allowed to pull in just from download?
I'm not sure.
Place?
I'd have to look into that. Do have quite a few, but yeah, not sure about that yet. But if not, then hopefully I'd be able to get it as a student.
It's pretty expensive. I mean, I think the program itself is like 40K, and then some of the databases are like 100K, and so it's expensive stuff.
So you're saying it'd be surprising if the lab had it if they weren't actively using it a lot?
Yeah, it's kind of an esoteric software. I mean, you're not talking like something that's similar to ANSYS or Abacus or those kind of really popular FEA packages. It's kind of weirder than that. It's often the woodwork more than that. There's fewer people who've heard of it. There's it's not real well known outside the materials community. I think with the Materials Genome Initiative, I think all of a sudden it's been maybe brought up to a little bit more prominence than it had been in the past, because the idea being that you can use the software to speed up development cycles in materials, which is, like I pointed out before, has been a problem. The lithium-ion batteries were sort of sorted out in the 80s, right? But we didn't have them in electric cars until when did the Model S come out? Like 2007 or 8 or something, or 2012. Sorry, 2012 is when the Tesla Model S came out. I don't remember when they got popular in phones and computers. It was probably before then. But I'm just saying, like, that time period is too long. So the government, the higher managers of the country look and say, wow, how can we speed this up? And all of a sudden they have these materials genome projects, and how do you do it? Well, Thermocalc is here. Has these databases. It has these models. You can calculate all this stuff out. All of a sudden, it looks a lot more popular. See what I'm saying? Yeah. Things move pretty slowly at Lincoln. So I would not be surprised if that is too short a time for us to have really got into it, or to have really spun up Group 74 and doing that kind of thing. So I'll take a look, and I'll use what I can. And if all I have is just the charts that are available online, then I'll see what I can learn from that. Okay. Well, have a good week. We'll see you next Thursday.
Great. Thanks.
If you have any other questions about INVAR, let me know.
All right. Will do.
Okay. Cheers.
See ya.